So please try to keep it to, oops, I need to do the screen sharing. So please try to keep it to 20 minutes maximum.
Hi, everyone. So it's great to be here. Thanks, Tom, for introducing the whole summer school legacy thing. Somebody has to. Okay, let's try again. Right, so I'm Edzer Pebesma. For those of you who don't know me, I'm a professor at the Institute for Geoinformatics at the University of Münster, where we hosted the summer school last year. And I'm also associated, I'm a member of the R Foundation. So if you have like questions about the R Foundation, then you could try ask me. Right, so the thing I wanted to talk about this morning is handling and analyzing vector and raster data cubes with R. So the data cube thing already came up briefly in Tom's presentation, where he said data cubes are raster data, right? So this is not the case. I will sort of make the case that's not the case. So who of you have seen this tidy data paper written by Hadley Wickham in 2014, right? Quite a few of you. So it's kind of the tidy data came the sort of whole tidy idea behind the tidyverse, which is a sort of an opinionated set of packages, mostly written by people who are now associated with RStudio, that sort of sets forward a particular way of analyzing your data, and it says what data should be organized tidy, for instance. Like this is a tidy data set. This is a socioeconomic data set coming from the PLM package, all data set. It's similar to the Gapminder data set that you might be more familiar with. It's like you have a set of regions and you have a set of times, typically years, and then you have all kinds of variables for the region. It can be a country or state for the region and for the year. And the way to do this tidily is to essentially have the full variable. So this is public capital, some highway measures, some water measures, to have the full variable in one column and have sort of the other properties in other columns. Yeah, so we have a column that tells where something is the case, when something is the case, and then what is particularly the case. Yeah, so this is a way that you could organize such data. That is very convenient for a lot of reasons, but in the end, it is basically you have all these variables essentially for every combination of state and year. Right, or that is essentially the question. Do you have, based on what you see here now on the screen, you can't tell, right? You would have to do the math. How many years do I have? How many states? Does that product kind of equate to the number of records I have? And then hope that all combinations are present. Another way of looking at these data is, for instance, as a three-way table. Right? That's an array. A two-way table, three-way tables, or multi-way tables are arrays. Arrays are structures in computer science where basically you lay out things along sort of along more than one dimension. Yeah? Along one dimension would be a vector. And so we have here the variable public capital that is laid out along the years in the rows and along the states in the columns. Yeah, so we have basically a matrix layout of that, and that has other advantages. And that is not tidy. That's the point that tidy data makes, that this is not tidy, and this is kind of leading to difficulties. And I'm arguing the other way, that this is also tidy, but leads to sort of very convenient structures. One of the conveniences is, for instance, raster data that are organized like this. Yeah, so you're not easily going to do that. So to jump directly to raster data, so I'm going to talk a little bit about this kind of data set. So I call these, well, these are just generic spatiotemporal arrays, but if once you're going to glue the vector geometries to the columns, to the states, essentially, then you have what I call a vector data cube. So that is an array data type where one of the dimensions is related to space, and that space dimension has feature geometries. Jumping to the raster data, you could look at, for instance, an RGB image, which is here, just a sample data set, an excerpt from a Landsat image somewhere in coastal Brazil. And if you sort of zoom on the top left 3x3 cells, just to make life a little bit easier, you see something like this. Although the colors didn't look very similar, so I'm a little bit at loss what happened, what went on here. But these are the sort of the first 3x3 cells here, and we see colors. Yeah, but the sort of the data, as you know, the data that underlies colors are 3 layers of red, green, and blue. So we have sort of thrown 3 raster layers on top of each other and combined them into the colors that they have. And if we would look at each of the layers, then we see that. And this is again a 3-way table, right? So we have 3 2-way tables of 3x3. So it's a 3x3x3 table of data that you can organize like this. That you can also organize like this, which is the array form that R has it. So the internal data structure where you have sort of the dimensions in place, but which you could also do in a tidy form as a data frame where you have the sort of the rows, the columns, the rows, and the bands, the 3 different colors, where X and Y are here converted into the corresponding geographic coordinates rather than the row and column numbers, yeah, which is usually more convenient if you want to interoperate spatial data. And then we have the intensity values for red, which is band 1, and for green, which is band 2, and so on for red, green, blue, the third one. So that is sort of the other way that you could look at, and of course all data you can sort of mold into this form, which has particular advantages and has particular disadvantages. The advantages of doing it this way is that if you have a couple of dimensions, then it easily sort of these kind of tables become very large and cumbersome to handle. And we know that raster data often has data that sort of varies over time. So we could have 2 X and Y dimensions, latitude and longitude, or X and Y in some coordinate reference system. And then we have a set of these layers that are all associated with time. Yeah, so it has become sort of fashionable to talk about a stack of these things. It's a stack, and then we think of raster stacks and so on. It has sort of the raster is so much everywhere that everyone now uses this terminology. Although there are also bricks, and nobody knows the difference. So we have a 3-dimensional data cube here, which is raster data and distributed over time. But we could also have the same things, but then for different bands, for instance, red, green, and blue. And then for different sensors. So our band would add a dimension. So we would have sort of on top row, we would have a 4-dimensional cube. And if we then combine it with another sensor, so on top we have Sentinel-2, on the bottom we have Landsat-8, and combine the two, then we would have a 5-dimensional data cube. Yeah, so dimensions crop up easily. Of course, you would have a little bit of work to sort of make sure that they have the same coordinate reference system and the same cell size and so on. And that is essentially what Marius Appel is going to talk about in the tomorrow session on the GDAL cubes. Raster data are not just sort of regular arrays with square grid cells. They can have sort of all kinds of forms that we also look at. They can be rotated where cells are still square but not aligned with X and Y. They can be sheared where we have sort of different alignments in different directions where the axes are no sort of the raster axes are no longer perpendicular to each other. They can be rectilinear where we have varying cell sizes along dimensions, and they can be a curvilinear. That means that in some kind of mapping to X and Y, they are a regular grid, but the mapping is entirely free. These are all kind of data types that occur in the wild, yeah, for whatever reason that this happens. Yeah, if you look at the download data, then you see that. Another thing, as I said, is the thing of vector data cubes, and using the same analogy of sort of 3-dimensional cube, you now have no longer X and Y aligned along these axes. Now you have a single spatial dimension, which basically lists a set of features, in this case, a list of regions along a single dimension, and you have other things occupying the other dimensions. That could be, for instance, the fraction of a particular land covered type, and you could look at a time series of that and have a 3-dimensional vector data cube. And this doesn't have to be sort of associated to regions, it can also be associated to points, where we also have coverage data, which is air quality, but we sampled it at a fixed number of locations and have station time series. Essentially, the stations is one axis. And those could be station ideas to make things simple. They could be also ideas with the features or with the coordinates associated to it. And then we could have different variables measured at these sampled stations, and then time series over the vertical, sort of giving that. And we will see that when we do analysis of raster data cubes, we quite often end up quickly with vector data cubes, because at some stage we want to sample things because we have training data somewhere, and we want to sort of pick the values from this raster data cube at points and then throw that in our machine learning trainings algorithms. So we have to sample them, then we end up with a vector data cube. We can also aggregate things, like here we have a time series of some kind of big storm hurricane thing passing over North Carolina. And then we could look at, for each county of Carolina, how much rain, how much precipitation fell at a certain amount of time. So we look at sort of the maximum precipitation within the county from these raster data cubes, and get sort of the maximum precipitation for each county as a time series. And we have vector data cube again. And you could sort of squeeze all these things together and look at sort of, for each county, when did the maximum happen? And we aggregate over time and sort of end up with a time value, and we could get something like this, which is sort of the whole aggregation of space and time of the raster data cube into a single vector polygon layer, where the attribute is now the time of maximum precipitation in this county. And so these are typical things when analyzing raster data kind of makes you end up pretty often by having to do certain assessments for polygons or for points for reasons. And then you could say, well, and I have to work with features and tables and so on, but you don't, quite often you don't want to sort of give up the other cube dimensions like time, right? And we'll still want to be able to handle time. And it is difficult if you want to do that in a table form. It's difficult to keep doing that in the tidy data form. That's not impossible, but it makes life a lot more difficult, as I will make the point. Am I at 20 minutes now? Oh, almost. So are there any questions? And we have time for one or two questions. So what will I do later this morning is basically explain this idea and demonstrate how these ideas were implemented, mostly in the package stars, which is for vector and raster data cubes, that builds on top of SF and the whole other spatial stack things, and go through a large number of examples, starting from very simple to more and more complicated examples, and show how things can be done and how things look, and what you can do or what you cannot do with that. Are there any questions left right now? Okay, thanks.
Okay, so thank you, Edzer. That was just a preview, a sneak preview of the basically his course in the morning. And now we have with us also Meng, who is a postdoc at University of Utrecht. And Meng will also like to present her talk. So please, Meng, 20 minutes. And this is just to motivate you. So we have another hall, which is on the end. And so you can also opt to go. Meng is a PhD student of Edzer. So she uses lots of this like a theoretical concept, but with the real live data problem, which is the global air pollution modeling. So I need to. Let's see. Okay, you ready to go? This one here. Okay.
Thank you. So good morning. My name is Meng Lu. I'm from Utrecht University, the Netherlands, and I'm currently working at the Global Geo Health Data Center. So today I'm going to talk about global air pollution modeling. About my background, I started from remote sensing and information engineering. And then during my master's study, I became really interested in spatial temporal data analytics. And that motivated me to join Edzer's group at IFGI. And I did my PhD thesis in spatial temporal change modeling for multidimensional arrays. So I worked on detecting change from satellite time series, satellite image time series from a multidimensional array perspective. So that means to jointly model change from the spatial, temporal, and spectral dimension to improve from independent pixel-based time series analysis. And we also did critical review about array-based models in geoscientific data analysis and management to understand, for example, how array-based models can contribute to a more efficient and scalable modeling process. And afterwards, I went to Utrecht University and kept on with spatial temporal data analysis. So my works are in remote sensing image analysis and the development of exposure assessment methods. For remote sensing image analysis, the themes are quite diverse, including like thermal image downscaling, foliage nation prediction, and also building delineation and many classification problems. And I'm mainly involved in the application of machine learning-based methods, and also to compare the machine learning and more conventional methods. And for the development of exposure assessment methods, I worked on agent-based modeling for for human space-time activities and the modeling of our environment, so primarily the air pollution. That has been my focus in the past 2 years and also the topic today. So I worked on the nitrogen dioxide, which is a highly traffic-related air pollutant. And our goal is to do global scale, high spatial temporal resolution mapping. So this is a bit ambitious topic, but we think it's a good time to get started because we have more and more relevant global data set, and they are with growing spatial temporal resolution and quality. Also, the data changes can be very exciting. So why is it so significant to do it globally? One reason is that in many countries, there's a lack of ground stations. So here, this figure shows the darker the color, the less ground stations there are. But in many of these countries, the people are like African countries, people are the most vulnerable to air pollution, especially children, they are suffering a lot. And so we need a good estimation there. And another reason is that it's essential for consistent epidemiological studies to be carried out worldwide. So why do we want to do it in high spatial temporal resolution? It is because like nitrogen dioxide and many other air pollutants, they are highly variable in space and time. So it's very important to capture the spatial temporal variability to more accurately assess the exposure. So there are in general two kinds of air pollution modeling methods. One is process-based, which tries to model the physical and chemical process of the emission, transportation, deposition process of different chemical species. And that include, for example, air dispersion models and chemical transportation models. But this kind of, but it is infeasible to do global scale, high resolution modeling with this kind of models because of the computation and input they need. And another is statistical based method. And that is also what I'm interested in. So this kind of method tries to find relationships between station measurements and predictors, such as transportation network, population, climate, elevation, and it can also make use of the output from process-based models or spatial temporal dependency. But there are not so many studies doing it at the global scale. So we did a preliminary study to evaluate different methods and data sources for the global model. So we compared different machine learning and linear regression based models to see if the non-linearities between the predictors and response can be better captured. And we also compared global and national models. So the national models, they are parameterized in countries with dense ground monitors so that so that we can better see the distance between the national and global model, also the heterogeneities between those national models. And we also separated day and nighttime models to see if we can to compare the models, and also it's essential for integrating human space-time activities in the exposure assessment. And importantly, we also evaluated the measurement from the Topomi instrument. So Topomi is on board of the Sentinel-5P satellite, which was launched in October of 2017, and it measures a very broad range of wavelengths and has much improved spatial resolution compared to its precedent satellite. So here you can see the amount of spatial information that can be reviewed by these two instruments. So here are some interesting results we found. We found that the machine learning-based methods obtain quite similar prediction accuracy across validation results, and so do the linear regression-based methods. So here I'm showing one from each group. Random forest from machine learning and lasso from linear regression model. So these bars indicate the root mean squared error. So the lower the better, and the orange indicate is for global model and the green for national models. So you can see that the random forest not only outperformed the lasso, but also the difference between the national and global models are smaller. So this is quite interesting because we commonly expect the national models to be better. Here's the spatial prediction at Phoenix area of Arizona. You can also see that the random forest gives some more realistic prediction patterns. You can see this more gradual dispersing pattern from urban to suburban areas. And it's not so clear from the lasso prediction. But we also found that despite the various machine learning-based methods and their national and global model obtain similar cross-validation accuracy, their prediction patterns can be very different. So here I'm showing 4 models that obtain almost the same cross-validation accuracy, but you can clearly see the spatial patterns are quite different. So that calls for better accuracy assessment. And we take a first step further by gathering more ground validation data. So we use the sensors on board of a cargo bag and then cycled it around a city of Netherlands, and then to compare again different models. So those are the preliminary results, and we also identified statistical challenges in the global scale regression problem. So, so how can we better model the spatially heterogeneous predictor response relationships? So for example, in different countries, there's different emission standards and they use different fields. So how can we capture these similarities between regions or country and the similarities within a region or country? How can we better model spatial temporal variability and integrate more spatial information? So most of the current statistical based air pollution models use the road density that cover there to represent the ground transportation network. So that is to calculate the road length within different buffers, but this has many limitations. So first of all, which buffer should we use? And then there's also drop lots of information. So for example, the corners, the roundabout, the traffic light, or multiple lanes, they may all affect the air pollution process. So can we go from the transportation network and automatically extract features to better model the air pollution? So we are currently doing temporally resolved and hierarchical based models, and specifically to develop methods that are based on mixed effect models and deep convolutional neural networks. So in the workshop, I'm firstly going to give an introduction about the air pollution modeling and the data we use. And then we are going to focus on the statistical modeling techniques. So I'm going to start from the example tree-based machine learning methods and see how they can be, why they are very useful. And then we are going to go deeper to see the improvements we can make. So how do we deal with overfitting? So what regularization and post-processing strategies we can use, and then to look at how to integrate more spatial information using deep convolutional neural networks. And last, we also look at modeling process in practice. So how do we adjust hyperparameters and do the cross-validation and mapping? So most of the hands-ons and scripting will be in R, besides the deep convolutional neural network, which is going to be in Python. So it's because of some benefits I see, and also I think it will be good if you learn deep learning in both R and Python, because we also have an R course. But you don't need to worry if you don't know anything about Python. So the scripts are quite easy to understand, and I'm also going to guide you through it. And for running the scripts, I'm going to share Jupyter Notebook through Kaggle. So that is open data platform for machine learning practitioners. So you get a computation place and that runs the Docker at its back. So you just need to run the scripts I share without installing anything locally or run anything locally. Yes, that's it. Thank you. So I hope to see some of you there. And if you can't come, I have the materials on this link. Yeah. Oh. Yes, that's a good question. So it measures the column density, and we use it as a predictor. So that contributes quite significantly to the modeling, and also we use the surface production from the numerical models from the Sentinel-5 as included.
So in your session, you want to work a bit like local model data, or you compare, or in your session now you're going to work with local or global?
It's on the global data. What do you mean global models? Oh yeah, we look at both.
Okay. Okay, so yeah, that's the main move, and you in the other room on the other side of this call, also be room, by the way, and so if you're interested in more applied aspect, so if you're more interested in the theoretical aspect, in the Edzer I don't think you're if you're more interested in the practical aspect, then probably may go. I think it's okay. And the last sneak preview is Christian Knoth. And Christian is also a postdoc from the group of Edzer. So you think it's you see it's a theme of the day. I think IFKI probably theme of the day. So please, Christian, tell us in 20 minutes what's your plan for today.
Okay, yeah, thank you very much for the invitation to share my thoughts here at this summer school. My name is Christian Knoth. As you see, my topic is going to be deep learning in R for the analysis of UAV-based remote sensing data. And in the tutorial or in this plenary, I want to kind of give a short outlook on what we will do in the tutorial, and I also want to answer the question why one would want to do that in the first place, because we have reasons to do or to be interested in deep learning others than that everyone's doing that these days. So we do have some reasons, and I want to explain those. And but before that, I was told that we should also say a few words about ourselves. So I'm a research associate at the Institute for Geoinformatics. I work in Edzer Pebesma's lab, just like a few other people that you are going to hear from this week. I'm also study advisor of our master study program. And yeah, my research interests are located in fields of remote sensing and spatial data science. And I know that this is a almost ridiculously broad term to put on such a slide, but it's rather accurate in my case because I don't have this one focus field that I focus on all the time. I've been doing all kinds of stuff. And if I wanted to narrow it down a bit more, then I would say that most of what I've been doing is remote sensing image analysis, often using high resolution data, and often in the fields of ecological monitoring or human rights monitoring. And one focus that has followed me for quite a while is the collection and analysis of UAV-based remote sensing data, which also brings us to the topic of this session today. So why deep learning for the analysis of UAV-based data? When answering this question, I would like to be a bit more specific. Most of you have probably already seen some form of this figure that tries to locate deep learning in the realm of machine learning or artificial intelligence in general. And what we will be using today are convolutional neural networks, which are a certain form of deep learning. So the question should rather be why CNNs or convolutional neural networks for UAV-based data. So we've been working with UAVs or drones, as some people call them, for quite a while. We started as a small student research group, and when we started, our vehicles didn't look much like this one, but rather more like this one. But it has been quite a development since then, and we've been working on many different studies, but we quickly found out that these tools are very powerful tools, especially for ecological monitoring. And this is also why when I talk about we, or when I say we, I basically mean that all these efforts nowadays are a close collaboration between the Institute of Landscape Ecology, namely Hannah Meyer's working group, and some people at the Institute for Geoinformatics. And we've been working on a lot of ecological monitoring studies where the objective often was to recognize or detect certain species, analyze tree species in forests, invasive plant species, or detect woody vegetation encroachment in swamps. And there are basically two properties of UAV-based data in relation or compared to satellite data that we always encounter when doing this, which is that we have a very, very high spatial resolution compared to satellite data, but on the other hand, we have a lower spectral quality, or as I put it here, consistency of the data. And I'm going to show this in an example. This is also the example that we will work on during the tutorial. So imagine we would try to detect patches of wildfire, which is these, let's say grass here, these grass patches. Then this is pretty easy to spot for us, but it's mainly because we're looking at kind of patterns of pixels. So if we look at certain patches here, we can easily differentiate between these patches when we inspect them. But the thing is that the pixel size is much smaller than the objects that we're actually interested in. So what we look at when we detect those as analysts are kind of patterns or patches of pixels. Because if we would look at single pixels only, then there are many areas in the upper image that would look very similar to anywhere else in the image, basically. So it's the spatial context that makes us identify certain objects in such high resolution images. And this is itself not a problem. So it's not a problem to have high spatial resolution. The question is rather how to efficiently use this high spatial resolution to detect things in images. And also, we might not even need this if the single pixels would carry a lot of information already for us. If they would have a lot of high spectral, or if they would have a high spectral resolution carrying a lot of spectral information for us. But when using UAV data, usually we have rather low cost or small sensors, for example, just RGB cameras, like in this case, or some self-built color infrared cameras. And there are nowadays more sophisticated sensors, also multispectral sensors that can be operated on UAVs, but still their quality cannot match the one that you would put on a satellite, for example. And even if another thing that we encounter with UAV-based studies is that spectral conditions can vary a lot during flights and between flights. So we don't have the usual problem that you have in remote sensing, that we need to do some atmospheric correction because we don't have a lot of atmosphere between the sensor and the surface. Most of the atmosphere is above the sensor, but still we are affected by different weather conditions. For example, cloud shadows, as you can see here in this example, where between two images in the same flight, while the drone or the UAV was just going a little bit further north, a cloud shadow disappeared that was there before, and that made the same object in the two images look quite differently in spectral sense. And you can, of course, try to correct for that by doing some pre-processing or applying some sophisticated classification. But it is an obstacle, an additional obstacle, and it can be complicated, especially when you have maybe both conditions in one images where they're partly shaded by cloud shadows. And in combination with the fact that we have this very high spatial resolution, this is the reason why it might be a good idea to look at texture and structure of objects or shape of objects and pay attention to the spatial configuration of pixels instead of only the spectral values. And this is exactly what CNNs are, so convolutional neural networks, are said to be pretty good at. So what CNNs do, or what neural networks in general do, is they consist of a sequence of layers that successively transform the input data into all kinds of different representations of the data, hopefully useful representations. And in the end, we will end up with an output, a representation that can be, for example, in a binary classification case, a number between 0 and 1, indicating whether or not there is an object, the target object in your image. And the specific thing about convolutional neural networks is that they don't just transform whole images and try to find patterns in whole images, but they're able to locally detect certain features and patterns in images. For example, certain edges or certain shapes or other pixel configurations, and they extract those features at different scales. And these features are then used by the successive layers to do the actual classification, which then ends up in our result. And we will talk about more how this works and how to do that in the tutorial. But this is mainly mainly the reason why convolutional neural networks are very popular in any kind of image recognition or pattern recognition task, and why they are also interesting for us in analyzing UAV-based remote sensing data. So when doing remote sensing, we are often not interested in whether or not there's an object in an image, but rather where in this image objects are, or the area that we are interested in are. So we want to do pixel-wise classification. And we can also do that with CNNs if we apply a according architecture that fits this purpose. And if we then kind of reassemble all these single subsets that we have analyzed to one map, we can finally get something that is similar to what we know from other remote sensing image classifications. So we put in a larger remote sensing image, and then we get as a result the map, in this case, of where wildlife, so the species that we're trying to detect, is located in this image. And in the tutorial, we'll mainly look at this, how to do this. So what actually are convolutional neural networks? How do they look like? And how to build them in R. So it's meant to be really a kind of introduction to CNNs. So we will try to understand the main steps involved when you want to apply convolutional neural networks. So we talk about how to build a network, how to prepare your data in order to work with this data in the neural network, how to train the convolutional neural network, and how to predict with this network, and how to do this in R. And we will also have at least an outlook on how to get from this image classification that tells you whether or not there's an object in an image to something that tells you where in a larger remote sensing image the target areas can be found, so which really does a pixel-wise classification of remote sensing images. And that's where we will try to get. And we will put main focus on really the basic workflow, so that you know how to do the basic steps of applying convolutional neural networks. And then depending on how much time is left, we will also give you some teasers about how to do this actual remote sensing image classification. But I will talk more about this in a tutorial. Yes. So there's a package. Yes, I will explain the package. It's rather new. Not. I mean, so we will use the Keras package, and I will also show you in the beginning a slide that gives a very short explanation of this ecosystem about. So we will basically use TensorFlow, and then there's Keras, which is an API for TensorFlow, still in Python, and then there's an R package called Keras that provides us access to this API. Yeah, we'll see if people are interested. So the examples I've used are really like small toy examples, so they should be even runnable on a. So they are runnable on my laptop, which is a really slow one. So I hope that you can try it out yourself too.
Are there any questions? Yes, here.
It was just actually regarding the installation. Not sure if this is a venue for asking a question.
No, it's okay. Installation. So the idea is that for each block, you have instructions inside the block installation. Today, I don't expect that you will have everything maybe running. So we have the evening session. You try your best to be able to follow. Otherwise, you can just see the demo. You see the demo, you get the idea where the things are. You have the instructions for installation. And then tonight, we're going to make sure everybody has everything installed. The first day, we always take the evening about 2 hours, sometimes even 3 hours, to make sure that for every other day you have everything installed, that you know where it is. But the idea is that in each block, you paste in this block, also you have instructions, what you need to install and what to use.
Yes, you found them, right?
Yeah, I found them.
You got a problem with that. Okay, let's see the data.
Okay, okay. That's not so now. You can ask me the treatment block. Okay. A question from the back.
Yeah, I was wondering, I saw the agenda, a few of the blocks of the session next
No, yeah, there are no repeats. There are some blocks, they are complex and they just take 4 hours. Some blocks are 2 hours and some are more complex, they take longer. And you will like that because you will see, for example, tomorrow, Marius, he has 4 hours It's a very complex topic, and he's very good at that. He made a package, but he will do it in 4 hours, so he will take really gentle steps, and that's why we have more time. And so that's I think it's good. It's a good thing. So there's no repetition, no. Yes. Yes, they build on top of each other. Yeah. So if you don't follow the morning one, it could get difficult to follow the afternoon session. Yeah. So you have to make a choice, and don't get too stressed. One more time, we have video recording, so you will manage to see. It's a difficult always when you do parallel. You have to make a choice. We cannot clone you, but we are video recording everything, and you can still join through Mattermost. You can ask questions, and you have access to all the slides. So in the coffee break, don't just drink coffee. Also, download the slides, look at the slides, and see what you're more interested. One more time, the main session is more practical, real data, practical problems. Edzer, I think more introduction and theory, right? Also practical. So yeah, so you have to choose. Maybe Meng is a focus on one specific data, and it's ambitious. You see, it's a global data set and space-time, hourly measurements, daily measurements. So there's lots of things. And then Christian also see very interesting multi-scaling, more complex machine learning. So it's super interesting. Okay, thank you. So this thing finishes our live broadcast. So thank you all for following online things. We see you in a bit more than a half an hour.